back in the 1979 or so, I was trying to build my first big computer system and trying to figure out, how should I represent computations at a high level? And I kind of invented this idea of using kind of symbolic expressions, structured as it's kind of like a function and a bunch of arguments. But that function doesn't necessarily evaluate to anything. It's just a thing that sits there representing a structure. And so building up that structure, and it's turned out that structure has been it's a good match for the way that we humans, it seems to be a good match for the way that we humans kind of conceptualize higher level things. And it's been for the last, 45 years or something. It's served me remarkably well.
So building up that structure using this kind of symbolic representation. But what can you say about abstractions here? Because you could just start with your physics project. You could start at a hypergraph at a very, very low level and build up everything from there, but you don't. You take shortcuts.
Right.
You take the highest level of abstraction, convert that, the kind of abstraction that's convertible to something computable using symbolic representation. And then that's your new foundation for that little piece of knowledge.
Yes.
And somehow all of that is integrated.
Right. So the sort of a very important phenomenon that is kind of a thing that I've sort of realized is just, it's one of these things that sort of in the future of kind of everything is going to become more and more important, is this phenomenon of computational irreducibility. And the question is, if you know the rules for something, you have a program, you're going to run it, you might say, I know the rules. Great. I know everything about what's going to happen. Well, in principle, you do, because you can just run those rules out and just see what they do. You might run them a million steps, you see what happens, etc. The question is, can you immediately jump ahead and say, I know what's going to happen after a million steps, and the answer is 13 or something?
Yes.
And the one of the very critical things to realize is, if you could reduce that computation, there is in a sense no point in doing the computation. Yeah. The place where you really get value out of doing a computation is when you had to do the computation to find out the answer. But this phenomenon that you have to do the computation to find out the answer, this phenomenon of computational irreducibility, seems to be tremendously important for thinking about lots of kinds of things. So one of the things that happens is, okay, you've got a model of the universe at the low level in terms of atoms of space and hypergraphs and rewriting of hypergraphs and so on. And it's happening, 10 to the 100 times every second, let's say. Well, you say, great, then we've nailed it. We know how the universe works. Well, the problem is the universe can figure out what it's going to do. It does those 10 to the 100, steps. But for us to work out what it's going to do, we have no way to reduce that computation. The only way to do the computation, to see the result of the computation, is to do it. And if we're operating within the universe, we're kind of, there's no opportunity to do that, because the universe is doing it as fast as the universe can do it. And that's what's happening. So what we're trying to do, and a lot of the story of science and a lot of other kinds of things, is finding pockets of reducibility. That is, you could have a situation where everything in the world is full of computational irreducibility. We never know what's going to happen next. The only way we can figure out what's going to happen next is just let the system run and see what happens. So in a sense, the story of most kinds of science, inventions, a lot of kinds of things, is the story of finding these places where we can locally jump ahead. And one of the features of computational irreducibility is there are always pockets of reducibility. There are always an infinite number of places where you can jump ahead. There's no way where you can jump completely ahead, but there are little patches, little places where you can jump ahead a bit. And I think, we can talk about physics project and so on, but I think the thing we realize is we kind of exist in a slice of all the possible computational irreducibility in the universe. We exist in a slice where there's a reasonable amount of predictability. And in a sense, as we try and construct these kind of higher levels of abstraction, symbolic representations and so on, what we're doing is we're finding these lumps of reducibility that we can kind of attach ourselves to, and about which we can kind of have fairly simple narrative things to say. Because in principle, I say, what's going to happen in the next few seconds? There are these molecules moving around in the air in this room, and oh gosh, it's an incredibly complicated story. And that's a whole computationally irreducible thing, most of which I don't care about. And most of it is, the air's still going to be here and nothing much is going to be different about it. And that's a kind of reducible fact about what is ultimately at an underlying level a computationally irreducible process.
And life would not be possible if we didn't have a large number of such reducible pockets.
Yes.
Pockets amenable to reduction into something symbolic.
Yes, I think so. I mean, life in the way that we experience it, one might, depending on what we mean by life, so to speak, the experience that we have of sort of consistent things happening in the world, the idea of space, for example, where there's, we can just say, you're here, you move there. It's kind of the same thing. It's still you in that different place, even though you're made of different atoms of space and so on. This idea that it's that there's sort of this level of predictability of what's going on. That's us finding a slice of reducibility in what is underneath this computationally irreducible kind of system. And I think that's sort of the thing which is actually my favorite discovery of the last few years is the realization that it is sort of the interaction between this sort of underlying computational irreducibility and our nature as kind of observers who sort of have to key into computational reducibility. Mm-hmm. That fact leads to the main laws of physics that we discovered in the 20th century. So we talk about this in more detail, but this is to me, it's kind of our nature as observers. The fact that we are computationally bounded observers, we don't get to follow all those little pieces of computational irreducibility to stuff what is out there in the world into our minds requires that we are looking at things that are reducible. We are compressing, we're extracting just some essence, some kind of symbolic essence of what's the detail of what's going on in the world. That, together with one other condition that at first seems sort of trivial, but isn't, which is that we believe we are persistent in time. That is,
yes. So some sense of causality.
Here's the thing. At every moment, according to our theory, we're made of different atoms of space. At every moment, sort of the microscopic detail of what the universe is made of is being rewritten. Mm-hmm. And in fact, the very fact that there's coherence between different parts of space is a consequence of the fact that there are all these little processes going on that kind of knit together the structure of space. It's kind of like if you wanted to have a fluid with a bunch of molecules in it, if those molecules weren't interacting, you wouldn't have this fluid that would pour and do all these kinds of things. It would just be sort of a free-floating collection of molecules. Mm-hmm. So similarly it is with space, that the fact that space is kind of knitted together is a consequence of all this activity in space. And the fact that kind of what we consist of, sort of this series of we're continually being rewritten. And the question is, why is it the case that we think of ourselves as being the same us through time? That's kind of a key assumption. I think it's a key aspect of what we see as sort of our consciousness, so to speak, mm-hmm. is that we have this kind of consistent thread of experience.
Well, isn't that just another limitation of our mind, that we want to reduce reality into some, that kind of temporal consistency is just a nice narrative to tell ourselves.
Well, the fact is, I think it's critical to the way we humans typically operate is that we have this single thread of experience. If you imagine sort of a mind where you have, maybe that's what's happening in various kinds of minds that aren't working the same way other minds work, is that you're splitting into multiple threads of experience. It's also something where, when you look at, quantum mechanics, for example, in the insides of quantum mechanics, it's splitting into many threads of experience. But in order for us humans to interact with it, you kind of have to knit all those different threads together so that we say, oh yeah, a definite thing happened, and now the next definite thing happens, and so on. And I think, sort of inside, it's sort of interesting to try and imagine what's it like to have kind of these fundamentally multiple threads of experience going on. I mean, right now, different human minds have different threads of experience. We just have a bunch of minds that are interacting with each other, but we don't have within each mind, there's a single thread. And that's that is indeed a simplification. I think it's a thing. The general computational system does not have that simplification. Mm-hmm. And it's one of the things, people often seem to think that, consciousness is the highest level of kind of things that can happen in the universe, so to speak. But I think that's not true. I think it's actually a specialization in which, among other things, you have this idea of a single thread of experience, which is not a general feature of anything that could kind of computationally happen in the universe.
So it's a feature of a computationally limited system that's only able to observe reducible pockets.